fascinating world of chemistry looking at the periodic chart. Periodic chart is representation of all elements by increasing atomic number, which we've already defined as a value Z. Now, the first chart was organized by this name. His name is Dr. Dmitry Mendeleev. He's a Russian, yeah. He was called the father of periodic chart because he first organized a chart. He used that using atomic mass and like character. Atomic mass, the A value, like character. Now, there were problems. There were holes all over the chart. And in Mendeleev's explanation, elements not yet discovered. Well, he was right. There were elements such as silicon and aluminum not yet discovered, but there was a problem. And so this guy came along, his name Dr. Henry Moseley. He's British, chip cheerio boy. He came up with the value Z. He discovered atomic number by using a cathode ray tube and calculus. Now, when it comes to elements of the periodic chart, there are three different classes we have: metals, nonmetals, and semi-metals. A metal is defined as anything that has luster, malleable, ductile, and conductive. What do those mean? Luster means it shines, malleable can be hammered into shape, ductile can be drawn into a wire, and conductive carry electric current. Nonmetals are dull, brittle, and insulative, which means they're not shiny. They are very easily, they break easily, and they don't carry electrical current. Now, a semi-metal are the elements that have qualities and properties of both metals and nonmetals. How do we find the periodic chart? Well, here's our periodic chart. We'll put a little line down the chart through here. Everything to the right of that is a non-metal, okay? Everything to the left of it is a metal. Now, the elements that touch on this line at all, those are semi-metals, okay? Now, we also have what's called a valence electron number. Valence electron numbers are defined as the number of electrons in the outer shell. Remember we talked about the outer shell, the octet rule, maximum number was 8 outer shell possible. So, if we look at the periodic chart to find the number of valence electrons, the first column, all of these have 1. Second column, all of these have 2. All the the D elements here, these also have 2. This column down, which is boron down, is 3. Carbon down is 4. Nitrogen down is 5. Oxygen down is 6. Fluorine down is 7. And from neon down is 8. Helium up here is also 2. And the 2F structures down here, these are also 2. All right, so let's say a silicon would have 4. Fluorine would have 7. All right, 2 more of the values. We're looking at ionization number and electron affinity. Ionization number is defined as the energy needed to lose an electron. Electron affinity is the amount of energy needed to gain an electron. In reality, for these, we're going to get a value called in kilojoules per mole. It's an actual number, okay? But because we don't know those, we're just going to make it simpler by identifying something off the periodic chart. So for ionization energy, since I have 1 valence electron here, these are our first. I can lose 1 electron easily. Since I have 2 here, all of these are first and second. Aluminum alone has 3, so it's first, second, and third. All right? All the nonmetals are zeros. Everything else is D and K. If it's not an alkali, if it's not a first, second, third, not a nonmetal, we say D and K. Everything else is D and K there. Okay, for electron affinity, okay? All nonmetals are yes, they can gain electrons. All metals are no, including the semi-metals, with one exception, the last column here, we call them noble gases. Those are also no. All right. Now, electron affinity, electronegativity. This is a scale between 0 and 4, the measure of the pull of electron. I'll give this to you. It's in your book on page 177. So do these. We'll do this in class. Shouldn't be too much of a problem. All right. So we also have something called diatomic elements. These are elements so electronegative they cannot exist by themselves as a single atom. So those are 7 elements. If they're by themselves, they're double. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. We call those the magic 7. All right, so on the periodic chart, these 7 elements are diatomic, but that's 6. Where's the 7th one? It's put over here. So if you can find that on the periodic chart, that's a magic 7. All right, now, we do have families and energy levels. Families or groups are columns of the periodic chart, identify columns. Energy levels are the rows, identify the size. All right, so let's look real quickly. First one, hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. These are all alkalis. Characteristics of them, they have 1 valence electrons, they're explosive, and they're extremely reactive. Okay? Alkalis, the next column over, beryllium, magnesium, calcium, strontium, barium, and radium. They are reactive. They have 2 valence electrons, not nearly as reactive as the alkaline, and they are exothermic. They give off energy. Okay? The transitional, the d orbitals, they all have 2 valence electrons. They're metallic, and their characteristics vary quite a bit. The boron group, carbon group, nitrogen group, oxygen group, all we have here is the number of valence electrons. Okay, so boron has 3, carbon has 4, nitrogen has 5, oxygen has 6. That's the only characteristic of them. Beyond that, they vary so much. All right, now, halogens. Halogens, the next to last group, fluorine, chlorine, bromine, iodine, acetylene. These are extremely reactive. They have 7 valence electrons, and they are poisonous. Last group, noble gas, helium, neon, argon, krypton, xenon, and radon. They have 8 valence electrons, of course, except for helium, which has 2. They're unreactive because they are filled shell, and they're all gases. Now, the last group we have there, all the way in the bottom, the F shells, those are rare earth. Rare earth have 2 valence electrons. They're rare, and they're extremely radioactive because they're so big. Now, real quick, copy these down. We'll do these in class. So hopefully this isn't a problem. Okay, take care. Be good. Bye.